and welcome to the Geomestic channel. Today's lesson is one of the big-ticket geometric concepts that you cover in a geometry class. Today we're talking about the famous Pythagorean Theorem. Before we get started, if you'd like to follow along and take some notes, click on the link in the description and you can print out a guided notes worksheet that will follow right along with this video. Now, Pythagoras was a Greek mathematician during the 6th century BC, and there's a little bit of controversy and mystery as to why he was credited with this theorem, because as we know from ancient Indian and Chinese, Egyptian and Babylonian texts, that this relationship that we're about to dig into was known hundreds if not thousands of years before Pythagoras was even born. And because it has been such a popular concept among mathematicians, it's been proven hundreds of different ways. One method that is kind of tangible and easy to wrap your head around for most people is this area model. So what I have here are two squares. Now these two squares, what I'm going to do is I'm going to tape them together. My two squares taped together here. And because they are squares, meaning all sides are the same and all angles are right angles, I'm going to give each square a length. So this side length we're going to call A, which means all the sides are A. And then this square, the side lengths, not A, we're going to be side length B. Okay, so we got square A and we got square B, where the side lengths are A, the side lengths are B. Okay, so we've taken the two squares together, and we know that the area of a square is simply just the base times the height, or length times width. So this square, the area is A times A, or A squared, and the area of the yellow square is B times B, or B squared. So together, these two squares have a total area of A squared plus B squared. Okay? So the next step, what we're going to do is we're going to take this length A. I'm going to use my compass here to make sure I've got the right length. So I've got this length A, and I'm going to translate it over here to the bottom of the yellow square, which is right about there. Okay, so that little mark that I made, that distance across the bottom of that yellow square is A, which then means that this distance here from this vertex of the blue square to that point is going to be the distance B. Okay, so what I'm going to do next is I'm going to take my straight edge and I'm going to draw a line from that point to the upper vertex. Make sure I get it right here. Upper vertex of this square. Okay, this length right here I'm going to call length C. And I'm going to do the same over on the other side. So that distance from that point to the top vertex of the blue square, like so. Now we do know that these two distances are in fact the same because we've got these two triangles here that we've created. And if you notice, you've got one side is A, the other side is B. Over here in this triangle that we created, one side is A, we said that this side down here would have to be length B as well. And since we know that these are right angles, these two triangles have to be congruent by side angle side, which means CPCTC, any other corresponding parts have to be congruent as well. So this distance being C also makes this distance over here C. Okay. Now the next step, what we're going to do is we're going to cut along these lines. We're going to cut these triangles off, and then we're going to rearrange this whole situation, and we're going to see what happens. Got my scissors here, so I'm going to cut along that line. And this one as well. So we've got our two congruent triangles, and you can see when we put one over top of the other, they are in fact the same. We've got our two triangles, and then we've got this thing here. And what we're going to do is we're going to place these triangles in in such a way that will create another square. There we go. Okay, so we have another square. And if you notice, with this square, the base is c, the height is c. What's the area of that square? C times c, it's c squared. And how did we get it? We took two squares with area of a squared and b squared, put them together, and we end up with a square with an area of c squared, meaning a squared plus b squared has to be equal to c squared. Okay, so this area model of the Pythagorean theorem is just one of the many ways that you can show that this relationship does hold true. So, go ahead and write it out here. Say the Pythagorean theorem in a right triangle, the sum of the squares of the length of the legs is equal to the square of the hypotenuse. That's what the Pythagorean theorem says. Okay, so if we see that that says the legs, which we'll call A and B, the legs are interchangeable. It doesn't really matter which one you list as A and which one you list as B, but the hypotenuse does need to be the C value. Okay, so again, in a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. Okay, now a common example of this is what we call the 3, 4, 5 right triangle. Okay, the 3, 4, 5 right triangle. So algebraically, this theorem states that a squared plus b squared equals c squared. So a, b, and c, I have values for the three sides of this particular right triangle, and if I put them in their respective spots, meaning a being 3, so a squared or 3 squared plus 4 squared equals the hypotenuse c squared, which would be 5 squared. We know 3 squared is 9, 4 squared, 4 times 4 is 16, and then 5 squared, 5 times 5 is 25. And wouldn't you know it, 9 plus 16 is in fact 25. So we can see that this holds true. 5 squared is equal to a squared, or 4 squared plus 3 squared. Now, we can use this relationship in many different ways. One way is just to confirm that a specific triangle is a right triangle, which is kind of what we did here. Anytime a squared plus b squared is equal to c squared, we know that it has to be a right triangle. But we also have kind of some ancillary properties as well that we can use to determine what other types of triangles you may have. For example, if c squared is greater than a squared plus b squared, this will give you an obtuse triangle. And if c squared is less than a squared plus b squared, that will give you an acute triangle. Okay, so this could be useful in a lot of different situations. Now, the greatest benefit of the Pythagorean theorem is it gives us the ability to find missing sides of right triangles if we know the other two. So let's take a look at that. So let's say you've got a triangle that looks like this. Right triangle, the two legs are 8 and 15, but the hypotenuse is missing. We don't know what it is. Knowing the relationship of a squared plus b squared has to equal c squared, we can plug in the values that we know and put in x what we don't know, and we can solve for that x value. So a and b, again, doesn't matter which one's which. I usually go the smaller one as a. So we'll say 8 squared plus 15 squared equals c squared, which we don't know. So we call that x squared. Okay, so we get to do a little bit of algebra here. 8 squared is 64. Woo. 8 times 8, 64. 15 squared. 15 times 15 is 225, which is equal to x squared. Add those two together, 64 and 225. That's 289, which is equal to x squared. Now what do we do from here? I don't really know, or I don't really need to know what x squared is. I want to know what x is, but how do I get from an x squared back to an x? Now in mathematics, most operations have an inverse, meaning you can get rid of things or undo things that have been done, and the square is no different. The inverse of squaring a value is to square root a value. If you watched the previous video, we talked about different ways to take the square root of values and simplify those radicals. But the opposite of squaring a number is square rooting. If we square root both sides, the square and the square root kind of take care of each other. And we've got x, and the square root of 289. You might not recognize that as a perfect square, but it is a perfect square. The square root of 289, what times itself is 289? And that is 17. Okay, so in this case, using the Pythagorean theorem, we know that x, that length of that hypotenuse up there, has to be 17. Let's try another one. Okay, same idea. We've got two sides of a right triangle known and one side that is missing. Notice though, this time we do know the hypotenuse. The hypotenuse here is 13, and it is one of the legs that we do not know. Doesn't change how we set up the problem. Still going to use this Pythagorean theorem relationship. In this case, A, we're going to call x, that's the leg here. The other leg is 12, so B, 12 squared. And then C squared, hypotenuse squared, is 13 squared. Okay, so you see the order is a little bit different. My x is on the left side of the equation. Again, no problem. 12 squared. 12 times 12 is 144. 13 squared is 169. This time, to get the x term by itself on the left side, we're going to subtract this 144 from both sides of the equation. So that gets rid of it here. We've got x squared equals, and then 169 minus 144, that gets you 25. And again, the last step, if we square root both sides, square and the square root cancel, we've got x equals, and the square root of 25 is just 5. There we go. Now, both examples so far, my value here at the end was a perfect square in both cases. That's not always the case. You don't always get these nice, neat numbers at the end, and that's perfectly fine. Depending on the problem, you might have to express your answer in a different way. But that's just the context of your problem. You just got to read your instructions. So let's try one where it maybe doesn't work out quite so nicely. Okay, we got x, 4, and 10 as our three sides. So if we identify a, b, and c, a squared plus b squared equals c squared, we'll call our a 4. So we got 4 squared plus b squared, call that x squared, and then our hypotenuse is 10. Hypotenuse is 10 squared. So 4 squared plus x squared equals 10 squared. Going through the steps, we'll square these out. 16, 4 times 4, plus x squared equals 10 squared. 10 times 10 is 100. Once again, we're going to subtract this 16 to get the x squared term by itself. So 16 is 0. We got x squared equals 100 minus 16 is 84. All right, last step here, we're going to square root both sides. And if we square root 84, you'll notice 84 is not a perfect square. And you might be okay just leaving your answer like that. X is equal to the square root of 84. Depending on your question, that might be fine. You might want a rounded decimal value. Maybe if you're looking at a length of something that you're going to have to measure and cut, if you get it to the nearest inch or nearest half inch, something like that, you might be okay. So if you were to type that into your calculator, the square root of 84, you would get something like x equals 9.165. And that might be okay as well. So both of these are the same thing. This is rounded. I would say it's approximately equal to 9.165. But your last option, which probably the most common way to go about these, is to take your radical. If it's not a perfect square, is to simplify that radical. Again, in the previous video, we talked about a couple different ways to simplify those radicals. I'm going to do it this way. So I've got the square root of 84. To simplify that, I've got the square root of 84. I'm going to break it down into two factors, one of which being a perfect square. So I know that I can divide a 4 out of 84, and I know 4 is a perfect square, so that's a good place to start. So if I take 84, 4 times 21 equals 84. So I've got this as 4 times 21, same thing as the square root of 84. I can break those two factors apart and say that's equal to the square root of 4 times the square root of 21. And since I know the square root of 4 is just 2, I can write this as 2 times the square root of 21. There's no perfect square I can divide out of 21. The only factors other than 1 and 21 would be 7 and 3, and those are both prime, so I can't really go any further there. So this would be the simplified radical version of the square root of 84. Again, all of these answers are fine. You might be asked to express your answer in a certain way, but that's just dependent on your instructions and what your goal is. All right, so that is the scoop on the Pythagorean Theorem, which is just the beginning of the realm of right triangle exploration. If you'd like to see what's next, consider subscribing to the channel, as this library of content will continue to grow each week. Hit the thumbs up button if this was helpful for you, and feel free to share it with somebody that you think may benefit from it as well. Thanks for watching. See you next time.